For many people, oysters are a tasty feature on local menus, but they're much more than that. Oyster reefs help prevent erosion, pollution, and create a home for sea life. New at 5:10 on your side, photojournalist Robert Rizzo takes us to an oyster reef installation using an innovative technique.
Somewhere off the coast of Florida, the state quietly dropped 500,000 tons of used oyster shells into the Gulf of Mexico. For most of the time it was happening, almost nobody thought it would matter. Then something surfaced on the seafloor near Cedar Key that none of the skeptics, none of the fishermen, and none of the scientists running the project had actually prepared for. None of this was engineered. There was no blueprint, no careful arrangement. What went into the water was leftover shell, scraped off plates at seafood restaurants, swept up by the ton behind processing plants, piled onto barges, and dumped offshore between 2007 and 2024. It was garbage, essentially, headed for a landfill and redirected into the sea instead. Nobody involved expected a scientific breakthrough. What grew there instead ended up rewriting the rulebook on how a broken coastline heals itself. The plan itself was almost embarrassingly simple. Collect discarded shell from around the state, load it onto barges, and drop it into the Gulf near Cedar Key. Over 500,000 tons went in before the program wrapped. And it's worth pausing on just how unglamorous the raw material was. No lab-grown substrate, no imported composite, just shells that would otherwise have been buried in a dump. That plainness is exactly why almost nobody believed it would lead anywhere. The backlash arrived immediately. Environmental groups called it dumping, wearing a conservation costume, warning the shell piles would smother whatever fragile life still clung to the sandy bottom. Fishing families who had worked those waters for generations warned of buried grounds, shifted currents, decades of local knowledge screaming that this was a mistake. This wasn't a fringe complaint. It was loud, informed, and coming from people who actually knew those waters. The agency running the program pushed ahead anyway, reasoning that the shells were headed for a landfill regardless. Worst case, you've just relocated trash. Best case, you've given the Gulf something it could no longer make on its own, a hard surface for life to grip. Here's the part nobody predicted. When survey teams went back to check the drop sites 18 months later, they were braced for disappointment. Silty mounds, maybe a few stray organisms, a long wait ahead. Instead, a shellfish specialist with Florida's wildlife agency froze mid-briefing reading the results. Life wasn't creeping onto those shell piles over the usual 2 or 3 years artificial reefs typically need. It was arriving in months. Whatever was happening down there had no real precedent in the scientific record, and figuring out why meant looking at something too small for a diver to ever notice. The real story started with bacteria. Within days of hitting the seafloor, microscopic organisms began coating the shell surfaces in living films. Not a random smear, but organized groundwork, laying the base for everything that would follow. The way footings go into the ground before a structure ever becomes visible above it. And the shells weren't passive raw material sitting there waiting. Oyster shell is mostly aragonite, a form of calcium carbonate that slowly dissolves in seawater, and as it dissolved, it released calcium that shifted the surrounding water's chemistry, just enough to make it easier for barnacles, tube worms, and baby oysters to latch on and start building. The shells were engineering their own colonization. A block of concrete or a sunken hull just offers a place to sit. These shells were reshaping the water itself while they sat there. And that double effect is what separated this sea floor from every other artificial structure ever sunk nearby. From there, it snowballed. Algae moved into the bacterial film within weeks, forming the base of a food web. Tiny crustaceans and drifting larvae arrived next, pulling in the first young fish behind them. Each layer built the conditions for the layer above it. A chain reaction assembling itself out of restaurant scraps with no outside push required. A stretch of open sand simply can't do this. It offers nothing to cling to, no chemical microzones, no structure. Not because life refuses to grow there, but because there's no starting point. The shells handed the system exactly the one ingredient it was missing, and it took over from there. By 6 months in, the shells were fully coated in layers of biofilm and algae. To anyone glancing at the site, it still looked like nothing, dull mounds, no visible drama. But the water samples told a completely different story. A functioning micro-ecosystem had assembled faster than conventional artificial reefs typically show any biological activity at all. That invisible layer was the scaffolding everything visible would eventually stand on. No bacteria, no shell chemistry, no biofilm feeding the first grazers, and there's no reef, just calcium sitting on sand. Oysters themselves need something hard to grow on, and that single requirement had been quietly strangling Florida's coast for decades. Larvae, known as spat, drift with the current searching for a surface to fasten onto, and they only get a short window to find one. Miss it, land on soft sand, and that's the end. In a healthy system, older generations of dead shell provide that landing pad for the next wave. A reef builds the platform for the next reef. But Florida's natural shell beds had been stripped away by decades of overharvesting, pollution, and coastal development, and once that foundation was dredged up or buried, the whole cycle collapsed. By the early 2000s, larvae were drifting through open water with nowhere to land, which meant no new oysters, which meant no new shell for the next generation. A loop the Gulf had no way to restart on its own. The dropped shell piles solved that bottleneck almost instantly, acting as landing pads positioned exactly where the current would carry drifting larvae. Within the first year, a researcher from the University of Florida's Marine Lab recorded juvenile oysters settling onto the new shell in numbers that blew past every projection. By year 2, those juveniles had matured and were releasing larvae of their own, stacking a second generation on top of the first. That's the moment this stopped being a human project and became a self-running natural process. People had chosen the sites and dropped the shell, but from there, nature carried it forward without another ounce of help. By year 3, researchers were counting roughly 847 oysters per cubic meter of shell, compared to almost none on the bare sand nearby. Same water, same current, same drifting larvae. The only variable was a hard surface to grab onto. One of the loudest opponents of the whole program was a charter captain whose family had fished those waters for 3 generations. He'd testified against it, certain it would ruin the fishing grounds his family depended on. In 2013, standing over one of the reef sites, he watched a thick school of redfish holding in the current around a shell mound, and admitted he'd never seen anything like it in 25 years on that water. That wasn't just one man changing his mind. It was the moment hard data and decades of lived experience on the water finally told the exact same story. Fish don't wait around once structure shows up where there used to be nothing. Within 2 years of the reefs taking hold, survey numbers near Cedar Key were so strong, the research team double-checked their own methodology, assuming an error. Fish biomass around the reef sites had climbed by roughly 340% compared to unrestored areas, and species diversity was up about 280%. Crucially, these weren't fish wandering in from somewhere else. They were juveniles being born and surviving right there in habitat that had never supported them before. The reefs weren't collecting fish, they were manufacturing them. Redfish moved in first, followed by sheepshead feeding on the invertebrates coating the shell, flounder working the reef's edges, and snook in numbers the area hadn't seen in years. Each species claiming a different niche, each niche making the whole system a little richer. That distinction between gathering fish and actually producing them mattered enormously to the scientists tracking it. Sink a shipwreck or a pile of concrete blocks and fish will show up to it. But you haven't created more fish, you've just given an existing population a new landmark to cluster around. The Cedar Key reefs were doing something categorically different, growing juvenile fish that would never have survived to adulthood otherwise. That's not relocation, that's population growth. Word spread fast among the people who made a living on that water. Other charter captains who'd once opposed the project were now formally requesting new reef sites near their favorite fishing grounds, the same agency they'd fought 6 years earlier. Hotels, bait shops, and waterfront restaurants started reporting real revenue increases tied to the marine activity around the reefs. What had been sold purely as conservation was turning out to be an economic engine too. Octopuses moved into the reef's crevices as dens. Sea turtles returned to forage. Dolphins started working the reef edges, hunting the dense schools that had gathered there. Every new arrival reinforced the food web underneath it, and the whole system kept getting more complex, more stable, and more resilient season after season. Meanwhile, something else was happening to the water itself that nobody had planned for. A single adult oyster filters somewhere between 30 and 50 gallons of seawater a day, all on its own. Multiply that across hundreds of thousands of oysters thriving across these reefs, and the whole system becomes a natural water treatment plant, processing billions of gallons daily, pulling out excess nutrients, bacteria, and farm runoff with zero machinery and zero electricity. The Gulf Coast has a chronic runoff problem. Nitrogen and phosphorus from farms and development feed harmful algal blooms that cloud the water and periodically trigger mass fish kills. The reefs were attacking that problem directly at the source, filtering out the very nutrients feeding those blooms. Within a few years, water clarity around the sites was measurably better. Oxygen levels were up, and the effect wasn't staying contained to the reef itself. It was spreading outward into the surrounding water. Clearer water let sunlight reach deeper, and that mattered because seagrass, critical habitat for juvenile fish, manatees, and sea turtles, needs that light to survive. As the water cleared, seagrass beds began reclaiming zones that had been too murky for them in years, and the grass then stabilized sediment and cut turbidity even further, letting in still more light. One recovery had triggered a second one. The filtration value alone was estimated in the tens of millions of dollars, the kind of cost you'd otherwise need serious mechanical infrastructure to replicate, running for free and improving every single year as the reefs kept growing. Word of Cedar Key's results spread through coastal management circles, and other states took notice. Alabama launched its own shell recycling program within a few years. Mississippi and Louisiana followed with large-scale reef efforts of their own, and the Billion Oyster Project in New York Harbor applied the same idea to one of the most polluted urban waterways on the continent, proving this wasn't just a warm Gulf phenomenon. Researchers started calling the underlying concept circular environmental design, the idea that material once written off as waste could be repurposed as genuine ecological infrastructure, not a stopgap, but a deliberate strategy with measurable payoff. Then, in September of 2017, Hurricane Irma slammed into the Gulf Coast as a major storm, with sustained winds over 150 miles per hour and a punishing storm surge. Nobody had built these reefs with hurricanes in mind, but the storm tested them anyway. When damage crews surveyed the coastline afterward, they found something striking. Shoreline protected by the restored reefs had eroded roughly 30% less than unprotected stretches nearby. The difference was visible from a boat. One stretch chewed up, the next one largely intact behind its reef. The dense, irregular structure of stacked living oysters broke up wave energy before it ever reached the shore, the way a jagged surface saps momentum that a smooth one would simply pass along. Engineers estimated the reefs had prevented roughly $3 million in property damage from that single storm alone, against a total restoration cost of about $5 million for the entire 15-year program. In one hurricane, the reefs had very nearly paid for themselves, and unlike a seawall, they cost nothing to maintain in the years leading up to it. A seawall starts cracking the day it's built, and only gets worse from there. These reefs work the opposite way. Storm damage exposes fresh surface, new oysters move in, and the barrier comes out of each storm a little stronger than it went in. That single data point forced a rethink across coastal engineering circles that had defaulted to concrete and steel for decades. Traditional hard barriers are expensive to install, constantly need maintenance, and often fail during the exact storms they're meant to survive. Traditional shoreline armoring can run into the millions of dollars per mile, while the Cedar Key reefs delivered comparable or better protection for a fraction of that cost, and the protection kept improving for free. By the early 2020s, these reefs had done something no artificial structure in the region had ever managed. They'd grown well beyond their original footprint, with the oldest sites roughly doubling in area with no further human input at all. Each generation of oysters settled, matured, died, and left behind shell for the next wave, building both up and outward like a forest that keeps spreading once the first trees take hold. Structural complexity kept increasing too. Crude mounds evolved into elaborate formations full of overhangs, gaps, and interlocking surfaces. each hosting its own microhabitat for crabs, octopuses, sea stars, and juvenile fish. Researchers also found these dense reefs were locking organic carbon into their shells and the surrounding sediment, a climate benefit nobody had originally set out to look for. Biodiversity at the most mature sites was approaching levels found on pristine natural limestone reefs. The gold standard nature normally takes far longer to build. The long-term trajectory points toward something restoration scientists rarely get to claim: a fully self-sustaining system that no longer needs human management at all. The people who dropped that first shell in 2007 could walk away entirely, and the cycle would keep running on its own biological momentum, likely for decades or longer. That outcome was unthinkable back when critics were calling it reckless dumping, and even the scientists running it were quietly bracing for failure. By the early 2020s, it was sitting right there in the survey data, visible from the deck of any boat that passed over the site. 500,000 tons of shell that restaurants and processing plants had thrown away, poured into the Gulf with absolutely no guarantee anything worthwhile would come of it. And look at what grew there instead.